Well, if you came here looking for self-compacting concrete explained in 60 minutes, you are absolutely in luck today. Why? Because we're going to take all that incredibly dense engineering and distill it down into just a fraction of the time. Honestly, we're skipping the usual agenda altogether today so we can dive straight into a genuinely fascinating mystery right at the heart of modern construction. We're going to break down the absolute essentials of self-compacting concrete, or SCC for short. By the end of this explainer, you're going to understand exactly how this totally silent, superhero-level technology is literally changing the physical world around us.
Okay, let's dive right into this. You know, for decades, the construction industry has been dealing with this massive, incredibly stubborn problem. I mean, if you've ever walked past a construction site, you've heard it, right? That bone-rattling, absolutely deafening roar of mechanical vibrators. The thing is, traditional concrete is stiff. When you pour it, it stubbornly traps all these little pockets of air. And if you leave that air in there, your concrete becomes weak, permeable, and frankly, dangerous. So crews have to bring in this heavy, labor-intensive vibrating equipment just to shake the air out and force the mix to settle. But what if you just didn't have to do that? What if you could pour incredibly strong concrete without ever vibrating it?
So traditional concrete is kind of stubborn, right? It's stiff, and it literally demands that heavy, noisy mechanical vibration just to settle into place. But this alternative, self-compacting concrete, it's practically a totally different species. It flows almost like a thick syrup or a heavy liquid, effortlessly navigating its way into every single corner of a mold. And the best part? It compacts completely silently under its own weight. Just by tweaking the material properties, this amazing solution instantly wipes out extreme noise pollution and drastically cuts down on the grueling, back-breaking manual labor we usually see on construction sites.
Seriously, the sheer scale of this shift really cannot be overstated. Industry experts have literally called this the most revolutionary development in concrete construction for several decades. It's not just a minor tweak, this is a full-blown paradigm shift. It was actually first developed in Japan simply because they needed to offset a growing shortage of skilled labor. They desperately needed a way to build faster and more reliably with fewer hands. And ever since then, the real-world impact has just been staggering. We're talking faster builds, gorgeous surface finishes, and a much safer working environment for everyone involved. So, how exactly do you make, well, solid rock flow like water? It requires this incredibly delicate magic trick of chemistry and physics. First up, you need a high powder content. We are talking super fine particles here, stuff under 125 microns. Second, your coarse aggregate, the crushed rocks, those are generally capped at a maximum size of 20 millimeters to stop them from causing blockages. And then, here's where it gets interesting, we add specialized chemicals, polycarboxylated ethers to actually make it flow, and viscosity modifying agents. Those basically act like a thickener to keep the heavy rocks from just sinking straight to the bottom. And these ingredients, they have to be perfectly balanced. Get it wrong, the rocks sink, the water rises, and the whole batch completely fails.
Which brings us to the real secret sauce. Now you might be thinking, hey, why not just dump more water in there to make the concrete flow? Well, any concrete expert will tell you excess water is the absolute enemy of strength. Too much water dilutes your cement paste and you end up with weak, porous concrete. Nobody wants that. That is exactly where superplasticizers come into play. These are new-generation chemical admixtures, specifically those polycarboxylated ethers we mentioned, and they act almost like microscopic magnets, literally pushing the cement particles apart. This gives the concrete incredibly high workability without adding a single extra drop of water. It lets the concrete act like a liquid while keeping its absolute structural integrity. It's brilliant.
Now, to turn all this cool chemistry into a practical, usable application, European engineering guidelines laid out some very strict criteria. You can't just mix this stuff up in a bucket and start pouring. For a mix to be officially stamped and classified as self-compacting concrete, it has to pass 3 non-negotiable requirements. First, filling ability. Basically, it has to flow and fill every single empty space entirely under its own weight. Second, passing ability. It has to squeeze through really tight obstacles without jamming up. And third, segregation resistance. It must stay completely mixed and completely homogeneous while doing all of that moving. Let's look at how engineers actually test these 3 golden rules out in the field.
Okay, here's the first major hurdle, the slump flow test. Now with standard concrete, engineers usually measure how far a cone of concrete slumps straight down when you pull a mold off. But SCC is so incredibly fluid that a downward slump tells us absolutely nothing. Instead, they measure how far the concrete spreads outward, horizontally, across a flat metal plate. To pass this test and actually prove its filling ability, that pool of concrete needs to spread out to a massive diameter of at least 650 millimeters. To put that into perspective, that's roughly the size of a large street manhole cover.
But hey,
It's not just about how far it flows, it's also about how fast it gets there. And that brings us to the T50 test. The second that cone is lifted, engineers start a stopwatch and they measure exactly how long it takes for the spreading concrete to hit the 500 millimeter mark. Naturally, a lower time means greater flowability. For a truly ideal batch of SCC, hitting that 500 millimeter target should only take a remarkably fast 2 to 5 seconds. Anything longer than that, and you know the mix is just way too sticky. And this next one brilliantly illustrates that second big requirement we talked about, passingability. The U-box test physically forces the liquid concrete to run an obstacle course. You pour it into one side of a U-shaped container, right? Then it has to flow all the way down, force its way through a series of super tight steel obstacles at the very bottom, and then somehow push itself back upwards into the other side of the container.
So why on earth do we test it like this? Well, because this perfectly mimics exactly what happens on a real-world construction site. SCC has to navigate incredibly tight spaces. In the U-box test, the concrete is forced through 13 millimeter thick steel rebars that are spaced just 35 millimeters apart. It is completely packed. If the crushed rocks inside the concrete jam together for even a second, the flow totally stops. Passing this test is absolute proof that the concrete can perfectly encase densely packed steel reinforcements inside a column or a wall, completely under its own weight, without leaving any of those dangerous air pockets behind.
All right, now for the third major hurdle, the V-funnel. This ingenious little device looks exactly like it sounds. It's a tall V-shaped funnel with a narrow little trapdoor down at the bottom. The funnel is filled right to the brim with SCC. Then, when the trapdoor opens, engineers time exactly how fast the concrete can squeeze itself through that narrow opening. This test is just a fantastic way to measure both filling ability and our third major requirement, which is segregation resistance.
So the really crucial point here is this. For a mix to get the green light, a flow time of 5 seconds or less is what's considered appropriate. If the mixture takes too long, say 10 or maybe 15 seconds, that is a massive red flag. It tells you the mix is unstable. It means the coarse aggregates, those heavy rocks, are separating from the fluid paste and they're piling up at the narrow opening, essentially blocking the funnel. And look, if that happens in a tiny test funnel, it is absolutely going to happen inside your building's walls. The V-funnel ensures the mix stays perfectly evenly blended together.
Okay, so with all this incredible chemistry and all this rigorous testing, you're probably asking, what's the catch? Well, it's the price tag. The raw materials for self-compacting concrete are actually 10 to 15% more expensive than traditional concrete. Those specialized new generation superplasticizers and viscosity modifiers we were geeking out over earlier, yeah, they do not come cheap. If you were just sitting there looking at a spreadsheet of raw material costs, SCC definitely looks like the significantly more expensive option.
But, and this is a big but, you cannot look at materials in a vacuum. Let's counter that raw cost right now. The overall economy of SCC is actually fantastic. Think about it, by using this material, you instantly eliminate the massive cost of compaction labor. You don't need huge crews of workers wrestling with heavy vibrators all day long. On top of that, construction times are significantly faster simply because pouring is so rapid. And furthermore, because SCC perfectly wraps around dense steel, architects can actually design much thinner concrete sections, which saves valuable physical space. So when you step back and factor in the massive savings in manpower, time, and heavy equipment, they far outweigh that initial 10 to 15% bump in material costs.
Which brings us to a final, really provocative thought. We've seen how this remarkable feat of engineering balances fluid chemistry to conquer physical obstacles, saving time, money, and quite literally, our eardrums in the process. With faster builds, vastly safer environments, and completely silent construction sites, is vibration just a thing of the past? As we gear up to build the megastructures of tomorrow, the loud, shaking construction sites we are so used to seeing might just fade away into history, entirely replaced by the quiet, unstoppable flow of self-compacting concrete. Thank you so much for joining me on this explainer, and hey, keep questioning the physical world around you.